So, let's see, that's page 528.
Okay.
Oh, good. Okay. All right, so they reference the comparison test. So I know if I look on page 525, they got the comparison theorem down there. So if I have if the function I'm looking at, let's call it g of x, if it's in between f and h, this is not the squeeze theorem, if you know the squeeze theorem, it's not quite the same thing. So if it's bigger than this function, and let's say that, let's do this one at a time, sorry. If it's bigger than some given function f, and the integral of f diverges, and the function I'm looking at is actually bigger than that function, what do you think its integral does? Diverges also. So it's sort of like the floor goes to infinity, so I'm going to go to freaking infinity. I don't have an option. So if the floor function, a function below me, its integral goes to infinity, obviously I must also go to infinity. I must also be divergent, right? So if this diverges, then integral g also diverges. And conversely, if I have a ceiling function that converges, there really is no way for me to diverge. If I'm always smaller than another function, so if I'm always smaller than h, where the integral of h converges, so I'm below the ceiling, and the ceiling, if it converges, and I'm always below the ceiling, there's no way for me to go to infinity, is there? I keep popping my head up against the freaking ceiling. So it keeps me contained. So one is I have a function that's below me always. This function here, that's me. I have this function that's always less than me. But that integral goes to infinity. Well, it's going to take me with it, right? It's going to push me along and say you're going to infinity also. And the other way is if I'm always below some other function, its integral converges to a finite number, I must also converge. Now this question here does not say actually do the integral. It just says tell me if it converges or diverges. Right? So don't start trying to do by parts or some weird thing here. It wants you to compare it. So your whole focus now becomes, can you come up with an easier function that you know is always below this or above this? And there's a part of this function that I can control. It's bounded. Who knows what the arc tangent looks like, the inverse tangent? Who knows what it looks like? Careful. So the tangent looks like this here, right? Wow. So the inverse tangent is just going to be that flipped. So the inverse tangent is always contained between negative pi over 2 and pi over 2. Right? Okay. Maybe. You guys with me so far? So of course, this is specific to this problem. I'm analyzing the function that I have and trying to figure out, is there something inherent in that problem that makes it bounded by something? Now that part should sound a little bit like squeeze theorem. If you don't know squeeze theorem, it doesn't sound like that. Sorry. So I could take so if this is my G is this, what is that always less than, for example? Less than or equal to, yeah. Yes, this will be always less than or equal to pi over 2 over 2 plus e to the x. Which means if I can show that this integral, so if my function is less than this dude, if this guy converges, then I must converge. Okay, maybe. So you take a look at that interval. So now we're going to look at the interval that's associated with. Does it make sense by itself that if I have a function that is always bigger than me, that function is always bigger or equal to me? Because this guy, his maximum is pi over 2. It's actually strictly greater than in this case, because it never gets to pi over 2. So I'm always smaller than that. If that guy converges, then so do I. I have to converge, because I'm always smaller than him. So if he adds up to a number that's not infinity, and my numbers are all smaller, then obviously I have to also add up to something less than infinity. I have to be convergent also. Okay, some of you guys have won you over a little bit. It takes a little while to sink in. So how would I start attacking this guy? And that's a much easier integral now. So now instead of doing that integral, I'm going to compare my function to what that function does. Much easier. I'll have some arctangent in there. I just have a pi over 2. It's awesome. So how could I do that integral?
Pi over 2 is just a constant.
Yeah, pi over 2 is just a constant. And actually, I could do something smart too. Let's see if we can do this. Here's something really kind of nice. What other part of that function do you wish you could get rid of? Let's see if you guys are at all near with me. That integral would be so easy to do because it's almost an exponential, but what's with it that screws that up? The 2, the stupid 2. If I did take that 2 away, I'm dividing by less, right? Let me say this again. This is kind of important because this is actually going to rule our world for a little while in some sections coming up very soon. Let me say this again. If I do write down that function, except I took the plus 2 away on the bottom. So now I'm dividing by less, which means my result should be bigger. So I made it bigger still. That is definitely bigger than that. Does anybody not trust me? Anybody not believe me? If I divide by something by 2 less than I was dividing by before, I get a little bit bigger than dividing by less, which means I got more of me left. Right? Maybe. That's the beauty of the comparison test, is that if you don't like a piece of it, you might be able to get rid of it if it actually keeps the inequality going the same way. Thankfully, it wasn't -2. That would have sucked. I couldn't really get rid of it then directly. Okay, maybe. But is every step here, is it true? This is definitely bounded by this. I could integrate this easier, but it's still, if I could get rid of that 2, it would definitely be a lot easier, because then it would just be e to the negative x, and that's simple. And I can, because I can make this less than that. So I have a function that's always bigger than my function, and if it converges, then so do I. So let's see what that thing does then. If it doesn't converge, we have to go back and do it the other way around. Maybe ours diverges, and I have to think of a function that's always smaller than me, that diverges. So what does that function do then? So I'm going to take this. I'm not going to calculate what this does. I'm going to compare it to what this does. Yeah, I'm getting tired of writing that pi over 2. So write the pi over 2 out. This will be e to the negative x. And in order to do this completely technically correctly, what do I have to do this integral? I love it. Limit as t goes to
0.
Infinity.
0 is okay. It has a finite out, but infinity is where this thing freaks out. So yeah, this will be pi over 2. Limit t goes to infinity. 0 to t. Now how do you integrate e to the negative x?
Negative e.
I love it. So I get pi over 2, limit t goes to infinity, negative e to the negative x from 0 to t. Pi over 2, limit t goes to infinity. What do you get in here? Negative e to negative t, minus negative, so plus 1, good. Be careful. E to the 0 is 1. That's where people should start making it 0, but those e's make it 1. But if I let t go to infinity, what do I get? Like pi over t times 0 plus 1, so I get pi over 2. Stop right there for a second. How we doing? Any steps we had trouble with there yet? If I let t go to infinity, what's 1 over e to the t? Right? It's e to the negative t? Yeah, so it's 1 over big, so it gets small. That's the key to this. So since a function that is always bigger than the function they gave me converges, the sum of the values of this function forever actually came out to be a number, pi over 2. Therefore, my integral must also converge. In fact, my integral sometimes goes negative, doesn't it? Well, not 0 to infinity. They had a bigger range. So yeah, from 0 to infinity, it's all positive. But the bottom line is it's got smaller values. So if these values add up to a whole number, there's no way in hell this could add up to infinity. It's going to be something smaller than pi over 2. It's definitely going to converge. That's why it's called the comparison test. Compare the function they gave you to some function that's bigger or smaller, depending on what you think this thing does. Now, just to give this away, I didn't say this earlier, but I had a feeling this must converge because e to the x gets small really fast. I mean, it's big, let me say it that way. So 1 over e to the x gets small really fast. So it seemed to have a really good chance to converge. That's why I wanted to compare my function with something that was bigger. If I think my function diverges, I want to compare it to something that is smaller and show that that guy diverges also. Okay, maybe. Yes. This is section 7-8, I think, right?
Yeah.
Yep. All right, cool. So this is we're gonna use a comparison test type thing with series, and we're gonna get a lot more into it. But I at least wanted to introduce the idea here, and hopefully, you remember squeeze theorem? Anybody never did squeeze theorem? Yeah, I gotta figure out what did you guys do? All right, sorry. Anything else from homework? Yeah.
11, number 18.
All right. Oh yeah. Okay. So this is a little bit freaky. Sometimes the really freaky sequences are the ones that look really simple. So they give us a sequence. Let's just start off at. So they want me to figure out a formula for the nth term of the sequence. So it's not obviously, without the zeros would be nice, because then it would just be multiplying by -1 over and over again. But that's not what it is, because the zeros are there, right? What else could this possibly be? So A1, for example, A1 is 1, A2 is 0, A3 is -1. So it looks like it's going down by 1, and then it turns. Then it goes up again to a certain amount, up to 1, and then it turns again. What function do we know acts like that? Yeah, cosine or sine, right? Cosine's a good option for this because this one starts at 1. And the nice thing, I want you to realize, sequences can use functions like cosines, but the thing with sequences is, what are they controlled by? That's a weird question. I'm not allowed to put anything I want to in there, right? That's the heart of a sequence. The first term, I want to plug a 1 in for n. The second term, I want to plug a 2 in for n. So I can have these otherwise continuous functions, but since I'm only plugging in certain values, I'm not going to get the entire cosine or sine. So you just got to figure out, how do I manage to pick off exactly what I want? So I want cosine of something, so it's 1. Cosine of, so this will somehow involve n is 1, and this will somehow involve n is 2. So it's probably going to involve some multiple of pi, at least in some way, right? You guys kind of with me? I'm thinking about stopping there, because it looks to me like not a lot of you guys have done this yet.
0, pi, 1 pi, 2 pi.
All right, so if it's cosine, if I start off with cosine of 0, that's 1. Cosine of, now where's it go to 0? Pi over 2. Where's it go to negative 1? Pi. So now you want to figure out how to write that so that when you plug a 1 into something, you get 0. When you plug a 2 in, you get pi over 2. When you plug a 3 in, you get pi. And actually, if you want to, let me see. I don't think they do this. It would be a little bit easier, but I'm not going to, I guess I won't go there. No, I won't go there. So more than likely, this is going to involve an expression. If I plug a 1 in and I want 0 to come out, so when n is 1, I want the result to be 0, it's probably going to have what expression inside? N minus 1. Sounds good, right? So let's think it's maybe it's n minus 1 times pi. Let's check it. When I plug a 1 in, I get cosine 0. Kick ass. When I plug a 2 in, did it do what I wanted to?
No.
Good. See, so now you just adjust it a little bit. So this is a part of the whole playing around with something to make it do what you want it to do, and not getting frustrated if it doesn't immediately do what you want it to do. I mean, don't expect yourself to get that lucky, right? So how do I adjust it? So if I leave it like this, cosine of 1 minus 1 pi would work, but cosine of 2 minus 1 pi, no good. So all I'm missing is, yeah, let's try over 2. Because then, so now those two are fine, right? So let's see, cosine of 3 minus 1 times pi over 2, that would be 2 pi over 2, which is pi. I mean, do you see how to develop this? The very first step we had to take was to realize that we're allowed to use, for example, trig functions. We're allowed to use any damn function you want to. And it doesn't have to be continuous because we're only plugging in 1, 2, 3. That's why I'm only picking out these certain values. But I know when I see that, the first thing I think is, it's a freaking trig function. It's got to be something, cosine or sine. And you could have used sine. You would have just had to adjust your inside, but it would have worked also. But cosine's a good one because it starts off like cosine does, right?
Section 7, number 20.
I like that. Sabat says we're done with that. All right, so 7, 7. Oh, this was 11.1. Yeah, that's where we did the sequences stuff. 7, 7, number 20. Oh, yeah, okay. So I really just assigned this problem just so you can see what those errors are. So if you look back on page, here we go, page 510. The error for the trapezoidal rule So let's look at the trapezoidal rule by itself first, because the a midpoint rule is basically the same thing, except it's half as much. It's got a 24 down here. So let's try to interpret what the hell this thing is saying. So if I only go so far out for the trapezoidal, so what I mean by that is if I only use so many rectangles. So if I use 5 rectangles, and not rectangles, trapezoids, n would be 5. We'll start there. Cool? So obviously the more trapezoids I use, what's happening to the error? Getting smaller. There you go. You guys kind of with me? Because I'm dividing by bigger. So of course the error is going to get smaller, which only makes sense. The more trapezoids I use, the better the fit should be, the less my error should be. So that's really what this says. The weirdest part about this really is the k, and the k is related to the second derivative, which is related to the concavity of the function, right? So this says that k is any number that's always at least as big as the concavity, the biggest concavity in there. Okay, cool. So to evaluate this error term, you first have to figure out what the second derivative of the function that you're working with is, and then figure out how big it gets on the given interval, right? So the example they give you, yeah, right below that they give an example from example 1, and then they have example 2. Cool. Yeah, the first one they did, example 1, back on page 508, was 1 over x. So let's look at that for example. Let's look at that. If my f of x is 1 over x, and I'm going from a equal to 1 to 2. A equals 1, b equals 2. So something like that. What's the second derivative of that? What's the first derivative of that? Yeah. And what's the second derivative of that? Thank you. Yeah, so it'll be positive 2, right? All right, that's not bad, right? By itself. So on the interval 1 to 2, when is this thing the biggest? Well, since it's 2 divided by x cubed, it's going to be the biggest when x is smallest. So this is always, on this interval, this is always going to be less than or equal to 2. Because at 1, it's 2, and then if I move away from 1, if I get bigger, it's going to get smaller. So the biggest it could be is 2. So my value for k would be 2. So that's the kind of work you do for the function they give you for that problem, to figure out what k is. And once you know what k is, you're golden. You know what b and a are. You know what n is, because they got to tell you. Right? They got to tell you how many trapezoids or whatever you got to use. So the rest of it's just plug and chug. The weirdest part to me is k. That's the one that really requires a little work. Do a couple derivatives, look at the function and see when is that going to be the biggest it could possibly be. That's what I'm going to use for k. Yes, ma'am.
How far down do you normally go before you realize where it goes to, or like the max it goes to?
How far down?
Or like how many derivatives do you take before, or is it like?
If you had to, you could do one more derivative to help you find the maximum for this, right? Because you can figure out whether the next derivative goes to 0 to figure out the maximum. In this case, it's the maximum occurs at one of the endpoints because it doesn't occur in the middle. Does that make sense? So it depends on what this function. This function is relatively simple because I'm just dividing by x cubed. So if x gets bigger, it's going to get smaller. So I'm not going to let x get any bigger than the smallest it could be. That's what I'm going to let k be. So this is called, this is error analysis. If I want to control my error to be less than something, it'll actually help me figure out, well, how many n's do I actually have to use? Because the more n's I have to use, the heavier the computation is. So the less n's I can use and still be within good levels for me, awesome. I don't want to use as many trapezoids if I don't have to. Of course, if I'm using a computer, I could probably use thousands of trapezoids. I could just munch it up all day, right? But even then, you want to know, do I need to use 1,000,000 trapezoids to get within 1 × 10⁻⁻10th centimeters of whatever this is I'm trying to get a hold of? I mean, I'm trying to machine something, right? Trying to make this more physical. Huh?
It's all the trapezoids.
All the trapezoids.
Like, use 9, just hold the 9 button down. That's the number of trapezoids you can use.
Could be. So anything, is that by itself? All right, so that's, I was hoping I get a question on that because this is a relatively simple thing to use. You know everything here except K. And they do explain to you and they do give you a couple examples, but it still might be kind of weird as to what the hell this K is. Where does it come from? And you look at the second derivative and you just got to pick any number that's bigger than that second derivative could possibly be here. So I could have used 3, 7, 114. To get a good estimate from here, I'm going to use the actual exact limit, the 2. Yes?
So would you always use, because you want to use the endpoint, at least, or the biggest endpoint one, so would you always just use the biggest?
Well, it depends on the function again. So if I had a sine function, right, if my second derivative was sine of x, and I was going from pi over 4 up to 7 pi over 6 or something, I got to figure out, okay, where in there is it maximal, and that's the derivative, the second derivative, where is it maximum, and that's the value I'm going to use. Does that make sense? So it totally depends on your function. This function was relatively easy to maximize. I just don't let x get big. I make x small, bam, I'm done. But it completely depends on what this guy is. If this guy is parabolic, then I just find, the maximum point. If it's a down parabola, it's going to be one of the endpoints. That's going to make it maximum. So you just really got to see what the second derivative is, and you can even just graph the damn thing, right? But you should be able to figure out what the maximum is from the function that you're working with. So the function you're working with in that problem, it was number 20, right? Siba?
Yes.
Is e to the 1 over x. So what's its second derivative? Let's take a look at it specifically. So looking at e to the 1 over x, what's f prime? This is going to be neat. I like this problem. How do you take the derivative of e? It's itself, e to the 1 over x, times, the derivative of the inside, which in this case will be negative 1 over x squared. How are we doing so far? All right, so this one is definitely just a little bit uglier than the example they gave us, as always. Because now what do I have to use for the second derivative? I have to use product rule. Good. So if I do this guy again, it'll be himself times another one of these. So it'll be, we stop there. Is that cool? If I take this guy's derivative, it'll be this. Pop. So multiply that by this e. So if I take this guy's derivative, it's that, and then one more of these times that, so that I get that. Please don't make me do more. All right. And then plus e to the 1 over x, and then what's the derivative of this? Yeah, okay. We already did it. So now this is the function you're looking at. How do I maximize this function?
Okay, so what we do like this. The second one would be negative 1 over x squared times
What's happening?
ex times derivative of the second one.
So this one is the derivative of this times this. And this one is the derivative of this times this. Cool. Okay. So who's got a suggestion? How do I find this guy's maximum? And we're on what interval here? Interval from 1 to 2. Well, think about it like this. What's e to the 1 over x doing as x gets bigger? As x gets bigger, what's e to the 1 over x doing? What's 1 over x doing as x gets bigger? Getting smaller. So what's e to the 1 over x doing as x gets bigger? All right. What's 1 over x to the 4th doing as x gets bigger? Smaller. Well, all right. So the whole damn thing is getting smaller if I let my x gets bigger. Of course, especially because I'm talking about from 1 to 2. right? Anything above 1, everything here is definitely getting smaller. So how do I make it the biggest? I don't let x get big. I make x stay as small as I can. And what's the smallest I can let x be? 1. Yeah, so it actually ends up being a lot like this one because it's got parts that look a lot like this. It's just not quite as simple to look at. Now you could do one more derivative, set it equal to 0, get the roots, and it would tell you if in there's any minimum. And you'll find out that no, there aren't. And then it's just one of the endpoints. That's the answer, right? So, there's a whole big purpose for all that crap back in Math 180. It's crazy. There's all kinds of places where you want to be able to apply those first and second derivative tests. And I know that would be the third derivative, but what am I trying to do to this function? I'm trying to maximize this function. So that is a function. I would take its derivative to investigate where its maxes and mins are, wouldn't I? Or you just graph it. Oh, you graph and calculator. Sure. So at 1, whatever the value is, that's what you want to let k equal. So if I plug a 1 in, I'll get, so f double prime of 1 is e times 1 plus e times 2. So I get 3. So that's going to be my k value. Good. That's the work you got to do to figure that out. So this is the kind of analysis you do for these processes, especially when we get to Taylor series, where if you just stop the 5th term, you'll be off in the 7th decimal place or something, and you got to ask yourself, is that good enough or not? For some situations, I could stop even earlier, but for other situations, I got to go way the hell out to be good enough. And it's not going to be exactly this, but it's going to be very similar to that to figure out the error. If you stop here, how big of an error could you expect? How much do you gain if you go a couple more steps out? Is it worth it? Those kind of questions. Okay, maybe. Some of you guys are just nodding. I like, stop talking about this. Just continue. I know that's what you meant. Okay, anything else from homework? Okay. And just real quick, if you've been going to the Math Study Center or to the upstairs tutoring center, please, dear God, if you have a bad or a good or whatever experience, make sure you fill out some kind of evaluation. They should have evaluations at both places. If you have a bad experience and you never say anything, you're just opening the door for other people to have a bad experience. So please fill those evaluations out. Otherwise, they can't do anything to improve things if you do. Or if you have a good experience, like I said, sometimes they give awards to tutors who get a lot of good evals. Right? So fill those out for that too. Okay. So I want to get back into 11. We're going to focus on 11.2 today. I want to go back to 11.1 real quick and make sure we finish that all up. Did anybody not get the handout from last time? Is that everybody? Okay. So last time we covered the front, most of this. We have to look. Oh yeah, we did the bottom two, right? That's where L'Hopital's comes back into play. Oh. Now, real quick, let me focus on L'Hopital's for a second. Some of you guys were telling me you really didn't cover it that much. Which, again, it's really crazy to me because it's such a powerful tool. I don't know what teacher would not tell you about this powerful tool, but oh well. So a very simple example. All right, so L'Hopital's helps me out with things that are otherwise impossible for me to tell anything about. For example, this one, what's happening in this one? As x gets really big, what happens to the top? Natural log of a billion, natural log of a trillion. That's getting, this is scaring me a lot. I'm getting scared. I am going to start crying. I really am. I don't want to. I don't want to. It's getting bigger, right? Natural log, it's... Natural log of x is doing what? Yeah. Okay. So the whole problem is, I really can't tell what the whole thing is doing. But the top is getting bigger. The top is going to... Okay, so I feel a little bit better. So I said just the natural log of x. The natural log of x, what's it doing? It's going to infinity. And the bottom is going to, obviously, infinity. So this is what's called an indeterminate form. So it's like worse than undefined. That's what I try to tell me. 1 over 0 undefined. 0 over 0, holy shit. Right? So because it's called indeterminate, it is in a form that I cannot determine the answer. Okay, so that's the only kind of thing L'Hopital's works for. So the mistake a lot of people make is they do it too much. They do it, and actually on the second step, it was determinate, but they kept going. If you apply L'Hopital's to a form that's not truly indeterminate, L'Hopital's step back and say, I don't know what's going to happen. That's all you, man. I don't know what the hell. So anything can happen. L'Hopital does not guarantee anything. So shit, I have no idea what's going to happen. So it only truly is guaranteed to work if I have currently an indeterminate form. So if I apply L'Hopital's, and L'Hopital's is all about the rate at which these things are going. They're both going to infinity, but if the top is going to infinity quicker, the whole thing would be going to infinity. If the bottom is going to infinity quicker, then the whole thing would be going to 0. If they're going to infinity at the same rate, they'll actually come out to be some finite number between 0 and infinity. Kind of nifty. So if I apply L'Hopital, so since it's all about the rate, I obviously will take the derivative of the top and the bottom. And this is where people, when I ask you to do quotient rule, people would just take the derivatives separately. And then when I say L'Hopital's, people would do the whole damn thing like it's quotient rule. This is not quotient rule. This is a concept. What's the derivative of the top? 1 over x. And what's the derivative of the bottom? 2x. And how can I simplify that? Is that indeterminate anymore? It's definitely not indeterminate because one of them is 1. So it's completely determinate. The bottom would go to infinity, so the whole thing goes to 0. Cool. So that's L'Hopital's. Anywhere we talk about limits of some expression like that, if it's indeterminate form, and you can write it as a ratio. So there are other indeterminate forms. There's 0 over 0, obviously. There's 0 to the 0 power. That's definitely freaky. There's infinity minus infinity. Right? People will look at that and say 0. Well, it depends. If he's going to infinity faster than him, it's going to go to infinity. You kind of with me? If he's going faster than him, it might actually go to negative infinity. Right? So again, this would be an indeterminate form. Okay, maybe. So a real quick example of that, and then we'll get into the new stuff. Let me see if I can make one up on the fly here. No, that's not one. Yeah, that is. There we go, Jeff. You can do it. That's not indeterminate. What do I want there? I want, there we go. Now it's indeterminate. All right, I feel better. So what form is that in? I kind of gave it away, but yeah, specifically it's 0 over 0. So it's indeterminate. What do you think I do here? Well, I could apply L'Hopital's here. But actually, I don't know why I made this one, but oh well, too bad for us. I know what I was trying to do. Oh, what would I do here? Who remembers this? L'Hopital's would work. But what else could I do? I could multiply by the conjugate, right? That would work. Let's try L'Hopital's. L'Hopital's is supposed to work if it's any indeterminate form. So I'll do half of it. I'll do the top. That was funny joke. Now you guys, how do you do the bar? I like it. So 1/2, let me just write like this, x plus 6 to the negative 1/2, right? Cool. I prefer power form instead of radical form, normally. But you can write however the hell you want to. What's most important, what's the first and most immediate way to rewrite this? Yeah, both of these, this is 2 times x plus 6 to the positive 1/2, right? They just both kind of come up. Is that cool?
So the other one is x plus 6 to the negative 1/2. It's in the denominator, but it's still negative to negative exponent. So this is 2
Yes, because this is x plus 6 to the positive 1/2. If I take its derivative, a 1/2 comes down, it goes down to negative 1/2. Yeah. So it is on the bottom, and now I can just take it up top. Now, is this indeterminate? No. When I plug a 3 in, I get 9. Square root of 9 is, times 2 is 6. Cool. So really, L'Hopital's was a little bit quicker than multiplying by the conjugate. A little bit, tiny. All right, how do we feel about that? I just want to make sure we're all on the same page with L'Hopital's, because it will come up every now and again. And if it's true that you never learned that, that's just kind of evil. Okay, so let's see. A couple things we didn't go over last time. On the back of this page, there's some stuff about some specific kinds of sequences. So if I told you that a sequence was, I said there's a sequence AN that's bounded above, and who remembers this? It's monotone increasing, so it's not strictly monotonic, but it's increasing monotonically, is another way to say that. Now think about what that would imply about this sequence. So one thing we always wonder about with a sequence is, does it converge or does it diverge? All right. The next section is going to be, well, if we add up all the sequence terms, does it converge or does it diverge? But right now we're just talking about the sequence elements themselves. So if it's bounded above, meaning not infinity, but there's some finite number that it never goes above, and it's always increasing, does it converge or diverge? Converge. Okay, good. So that's part of what this is saying. So a lot of what this is saying is actually really, truly common sense, right? Can't say that a lot with Math 280, but I can say that about this. It's just that you're not used to the symbols that we're using, the terminology that we're using here. Blah, blah, blah. So we already talked about monotonic and strictly monotonic. What was the difference there?
One was going like straight, and the other one like kind of.
So monotonic, it must always be either not decreasing or not increasing. But monotonic means it could be flat sometimes. Strictly monotonic means it is strictly increasing or strictly decreasing. It's never flat. Kind of with me? So that monotone means, it sounds like monochrome. One color. So that would mean one direction. Not the band. Blah, 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 blah. Just want to make sure I don't miss anything. So this is kind of silly. So that's the theorem 12. Every bounded monotonic sequence converges. And that's a specific example of that. But it only kind of makes sense. If I tell you sequence is bounded, and if I just say bounded, it means bounded above and below. So here I said bounded above. But if I just said it's bounded, that means it's bounded above and below. So if I know it's bounded and it's monotonic, there's no way in hell that it could be anything other than convergent. In fact, if it's bounded, it's going to be convergent, period. So in every non-decreasing sequence that is bounded above converges, just like that one did. All right, so that should all be... Yes, sir, yes, sir. Shouldn't be too crazy.
If it's bounded above, could it still be divergent towards the negative?
Exactly. So that's why you have to add in there the fact that it's increasing.
Okay.
If it was decreasing, then why it wouldn't give a shit about this. It's just say, I am gone. Yeah, so it's got to be, and then if you turn around, then you're like, well, of course that's true. If it's going up and it's bounded above, it can't diverge. It can't go to infinity. It's stuck, right? So here's where it gets more interesting. So let's look at part A here down there at the bottom. Can you write an expression for AN? And this is actually a little bit less than before. This is actually, you want to define this, how do I say? There's obviously no real constant thing I'm doing. I'm not always adding the same thing. I'm not always multiplying the same thing. You with me? Is that true? You guys with me? All right. But what am I doing? The first term is 1 over 2. The second term is 2 over 3. So the tops are always n. And the bottoms are always... All right, good. So sometimes rewriting a sequence as the anth term, the general term form for that is simple. Don't overthink it. People get stuck with this thing. What am I adding there? Let me subtract those fractions. And no, it's just you can just define it directly. You with me? So the first, second, third. The third term would be 3 over 4. Bam. So what about here? Try part B. Oh, I'm sorry. That's number 1. What's number 2 say? Number 2 is determine if the sequence is monotonic, strictly monotonic, or neither. So what do you think about this sequence? In which direction? Is 2/3 smaller or bigger than 1/2? Bigger, right? And it's going to hold forever. 3/4 is bigger than 2/3. 4/5 is bigger than 3/4. You with me? Okay, that's very true. So it's strictly monotonically increasing. Strict mono increase. That sounds like a really bad medical prognosis for a community. Determine if the sequence is bounded above and or below. So since this is strictly increasing, it's obviously bounded below by what?
1.
Okay, 0 does work. 1 does not work.
Below 1/2.
Be more specific. Yeah, 1/2. It's bounded by 1/2. So 0 technically is true, right? You can say that's the floor and it's sitting up on the table. But the table itself would be 1/2. It never goes below 1/2. So it's bounded below by 1/2. Is it bounded above? So if it's strictly increasing and I want to see if it's bounded, I let n go to infinity and see what happens. And of course, n goes to infinity, this becomes 1. So it's bounded above by 1. It never gets there, right? It would be a horizontal asymptote for this guy. Do you guys see that? Do you see how all this math is suddenly coming together? Stuff you learned back in pre-calc suddenly is coming back. So it's bounded below by 1/2 because that's where it starts and it just goes up from there. It's bounded above by 1 because if I let n go to infinity, that's the limit. So it's never going to go above 1. So of course, obviously this thing, does it converge or diverge? Convergent. Of course, we know it converges to 1. Yeah, it never gets there, but the limit to infinity would be 1. So that's what it would converge to. Cool. All right, that's the whole thing. So try part B. Same questions. They're all right there on the sheet. That's not too bad there. Oh, it's the one from the last time. Did you get that? No? Oh, yeah, okay. No worries. All right, so who's got the nth term, an? What would that look like? It's hard, right? What about, what kind of sequence is it? Monotonically? So, yeah, good. So strictly mono decrease. That sounds better. Bounded above and below? Above by 1? Below by 0, because if you let n go to infinity, this is going to go to 0. All the terms are obviously positive, and they go towards 0. So it's bounded in both directions. It's just bounded above and below.
Converges to 0.
Yeah, it converges specifically to 0. We can see that. We just take the limit and show that. All right. So obviously they're going to get a little bit worse than that. That wasn't too bad yet. All right.
What does that say? Converges to
0. Sorry. Yeah. Let n go to infinity. This thing's going to go towards 0. Okay, so today we're doing something called, well, we're getting into series, which again is when I take sequence elements. So sequence would be terms separated by commas, right? 1, 4, 7. A series would be those terms separated by pluses, and you add them all up, right? So a series is the sum of all the sequence elements. Okay, so sometimes that will converge. Like if my sequence was 0.1, 0.01, 0.001, we saw that would converge to 0.1, which is 1/9. You kind of with me? So sometimes they definitely will converge. When people first hear that a series is adding an infinite number of terms up, they completely disagree with me that it'll converge. But hopefully I showed you that example already. Just keep that example in mind. That's exactly how something can converge. If it gets out of its own way. If it goes to the next decimal spot quick enough, it'll converge to a finite number. So let me give you this. This is from section 11.2. Anybody ever heard of something called math induction? Anybody? Sounds like a procedure you would go through in a dentist's office or something. Or torture. You get captured by terrorists. They connect something to a battery and do something to you. No, I'm not going to do that.
You like write math on a piece of paper and like shove it under your skin.
Yeah, exactly. Say, I want to take them out if you can solve the problem on them. Oh, God.
Can't even see the problem.
Alright, so do me a favor. Don't look at this too much yet. I know you guys are going to look at that, and it's kind of good. That's one reason why I gave this out, was so you can just kind of glance at it. Don't try to make too much sense out of it yet.
Can you help us do A of n of C on that?
Sure. Well, C, real quick. C was, on that worksheet, C was 147. So what would A n be? I know I had this up here before. I can't remember if we did A n for it. A1 is 1. A2 is 1 plus 3. A3 is 1 plus 6. So 2 3s. So A2 is 1 plus 1 3. So A1 is 1 plus no 3s. So this is all about taking steps away from something. So if I'm at 1, I haven't taken any steps yet. If I'm at the second term, I've taken 1 step, that's 3 big. Then I take 2 steps, that's 3 big. So forth. This is what's called a geometric sequence. I'm sorry. Geometric is multiplication. This is called an arithmetic, A for addition. So what would A n be then? If A1 is 1 plus 0 times 3, A2 is 1 plus 1 times 3, AN is 1 plus n minus 1 times 3. And then you can simplify that to be 3n minus 2. Is that cool? Distribute the 3. So some of you guys might realize if you add 2 to each of these, what do you get? If you add 2 to each one, what do you get? 3. Just add 2 to each one, what do you get? 3, 6, 9, 12. Does that sound familiar? Yeah, so that's why it's 2 off from being multiples of 3. That's really what that says. So you might have seen that first. It's not the first thing I would see there, but you might see that's the first thing I would see somewhere else. But here I didn't see that first. But if you see that, they're just, every one of them is 2 off from a multiple of 3, you can go straight there. Kick ass. That's the definition of every element. It's 2 off from its multiple of 3.
Is that the same thing as 1 plus 3n? Is that
No.
If n starts at 0?
If I started it at 0, which actually you're allowed to do. But for some reason in this section, I'm trying to keep true to this section. They don't start at 0. When we get at 11.2, you can start at 0. So if I started at 0, this would totally be 1 plus 3n, period. I lock it. Which makes more sense to me, because if I haven't taken any steps yet, I should be at the 0th spot. Then I take 1 step, I'm at A1, right? Cool. Okay, so, let me ask you this. I think I've shown you this. No, maybe I haven't. We haven't talked about the urban legend for mathematics, which there are some. Wouldn't make for a very good movie. But there's an urban legend about Gauss. His grade school teacher was getting upset about everybody just yelling. And it took me for Calc 1 to know this. But maybe some other people told you. And he said, add up the numbers 1 through 100. And that'll keep you little snots busy. And he sat there reading the paper. And Gauss took about 10 seconds, brought it up to him, said, there you go, man. So he had to sit down and do 1 plus 2 is 3 plus 3 is 6 plus 4 is 10. He had to, and he's like, yes, you're right. How did you do that so quickly? So, of course, who knows what they did? What did Gauss do? Anybody know? What's the rule? Yeah. 1 plus 100 is? 2 plus 99 is? And how many 101s are you going to have? Yeah, 100 divided by 2, you're going to have that many pairs that add up to be 101. So 50 times 101 comes out to be the neat number 50-50. So that's what you get when you add up all the numbers from 1 to 100. So in general, if I have a sequence, and this would work for 1, 4, 7, 10, as long as it's going up by an equal amount every time. This one goes up by 1, that one goes up by 3. I can use this expression for the sum. So if I have an equals 1, 2, up to n, so A100 would be 100, and I want to know S100. Well, now we know that's 50-50, right? So I just want to introduce these symbols to you. So we're already used to A1, A2, A3. S100 is called a partial sum. Why would I call this a partial sum? Because how far could n go? Forever, and I just went part of the way, right? So it's a partial sum. So I could have the 100th partial sum, the 200th partial sum, so forth. Are you with me? Okay, I'll take that as yes. There's one person saying yes. So that's the symbols for what we just did there. So in general, Sn, for any sequence that looks like this, where they're separated by the same amount. You can do this for 1, 4, 7. You can do this for 1, 5, 9, 13 if they're separated by 4. They just have to be separated by the same amount. You can do this. It'll be the first term plus the last term times the number of pairs. That's the idea, isn't it? You take the first term plus the last term, add them together. That's the sum that's going to repeat over and over and over and over as you step in, step in, step in. And how many of those will there be? N divided by 2. If you have an odd number of numbers, that just means you're going to have one number in the middle that's its own self. It doesn't pair with anybody. Aw, right? Poor little dude. Okay. So what we're going to do is we're actually going to use math induction to prove this, just to get used to what math induction does. So we have effectively proven this already, but I want to start with something that we know and at least can see why it works, and I want to show you math induction through it. I want to show you. So math induction can prove insanely difficult looking statements. It can prove it. And the evil thing about math induction is you don't trust it. It doesn't feel like you're allowed to do what you can do with it. So let me ask you this, before we get into this. Can you guys, I don't know where I'm from. Can you guys imagine if I had, it'd be cool if I brought this, a bunch of dominoes set up, right? We're going to knock them over. You with me? I have a bunch of dominoes set up. You're going to knock them over, some idiot comes in, no. If I could prove, stay with me now, watch. So I have a bunch of dominoes here. If I could prove that if any domino falls over, the next one will also fall over. Are you with me? If I could prove that if any domino, say the kth domino, right? There's n dominoes, and I want to look at the kth one. I'm saying that on purpose because that's what we do in the proof. The kth one could be the 7th one, the 8th one. K is just my middle of the sequence variable that I use. You with me? So if I can show that if that one flips over, the next one will also. And if I show that, and if I flip the first one and the next one falls, I've proven that they all fall. I've proven that if I can flip this one down and it knocks the next one over, and if I prove that if any of them fall, the next one falls, then they all must fall. Now just sit back and you're all like, what does that have to do with Cal 2? Just keep that idea in your mind, because I love the idea of dominoes. This is exactly what this is all about, in a way. Okay. It's one of my favorite things, by the way. And you're like, that doesn't make me feel better. All right. So here, let's look at Gauss again and what he said. So he said specifically, if I have 1 plus 2 plus 3 plus 98 plus 99. Let me see. Let me do this more. Yeah, let me do this in general. Sorry. Plus n minus 1 plus n. Let's not do it up to 100. I want to do this more generally. So if I add 1 up through n, what did we just say we should get? We should get n over 2. And 1 plus, n. I like it. In this case, a sub n will be n. It's very cool with what I've written there so far. That's exactly what we were saying earlier. Is this true? I mean, earlier we just had specifically 100, but now I'm just saying go up to any n you want to. Okay, where's my blank? So here's how this works. I want to do what's called a base case. Prove it for the first element, right? So if n is 1, this is my base case. Sounds something like from psychology, but that's basket case. That's different. So if n is 1, what does this statement boil down to? If n is 1, how far up do I go? I go up to n. Well, what's n? 1. So I get 1 up to 1. Okay, 1 equals 1/2 times 1 plus 1. Is that true? 1 equals 1. Check. So that's knocking the first domino over and seeing that it does knock the second one over. So I've established that the first thing, the first possible element works. The first domino does knock the second domino over. Now here's where people really get disconnected from this. I want to now prove that if I'm looking at the kth statement, what would the, you just gotta love that. Sounds like a list. What's the kth statement? And in the general it's called SK. The kth states, the kth sum in this case, and it's not always sums. That's why I don't like that notation, but too bad for me. What would the kth statement say? Don't worry, this is the nth statement. So what would the kth statement say? 1 plus 2 plus ... plus k equals k over 2 times 1 plus k. All right, that's amazing. And trust me, when I first learned this, I'm like, why do we have to do that? It's the stupid thing with n's, just with k's in it. But obviously I've kind of turned a leaf there. Sorry. So we got to establish that it's true for some k that's in between 1 and n. So it's true for the kth domino. So, and actually we assume this is true. If I can show, so assuming that a domino here will fall, if I can show that that means the next domino will fall, then they all will fall. Okay, maybe. So assuming this is true, I want to show that sk plus 1 must be true. So I assume, this is where people have trouble. They say, how can we assume this shit? Well, can anybody tell me, why can I assume that? I can assume that because I know it's true for 1. So at least this S1 works. Now what I'm about to show is, if it's true for the kth one, it must be true for the k plus 1th one, which automatically means is true for every damn thing. I don't know if you guys understand that step I just took. If it's true for the kth one, and I show that that means that it's true for the next one, well then it's true for everything. That one thing I did was so powerful. If it's true for any of them, it must be true for the next one. That's what we're about to prove. Which means then the whole damn thing is true. Because if it's true for the first one, it must be true for the second. If it's true for the second one, it must be true for the thank you. Right? All the way down. That's the heart of math induction. But it just feels like you're cutting corners, and it just feels like it's not legal. But it totally is. It's crazy. Now, I've got to be careful here. So assume that sk is true. Assume that the statement with the k in it is true. I want to show that. Let me introduce this symbol here. We want to show, that's going to save me so much horrible writing. We want to show sk plus 1 is true, assuming that sk is true. Now what would sk plus 1 say? Let me put this in parentheses. Sk plus 1 would say what? At least you're with me. What does n say? 1 plus up to plus n. What does k say? 1 plus up to k. What would sk plus 1 say? 1 plus blah 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 plus k plus 1 equals. Beautiful. Just replace every k with k plus 1. What would be on the inside? Alright, so everybody see where I got that from. That's what we have to show. Are you with me? I can't say this is true yet. This is what I need to show is true. So assuming it's true for some kth term, I need to show then that that implies that the next one is true. The minute I can show that, that means every damn thing is true. Because I already showed it's true for 1. If I can show that any one is true means the next one is true, it goes right through. Dominoes, falling back, whole thing's good. Maybe. This is definitely a freaky but powerful proof method. It's just stupid awesome. And you guys are like, all right, dude, shut up. So if I start with sk, so here I have to do the proof now. So I established what I'm going to assume. I've written what I'm going to have to show. So start with what I know is true. I know sk is true. How do I know sk is true? Because I assumed it to be true. Right? So sk says 1 plus 2 plus blah, 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 plus k equals k over 2, 1 plus k. Now, how do we get to, what's another way to get to k plus 1? I can just do what to both sides? What's this missing? Plus k plus 1. So I'm going to add k plus 1 to this guy. If I add it to that side, now I know this is true. I know this equality is true, right? So if I add something to this side, I have to also add it to the other side. Now here's the next key thing to realize. I know what this side should look like for the k plus 1 term. If I add this to this side, I have to make it look like this. If I can do that, I'm done. I've proven it. I've shown that this guy, if I start with this guy, it leads to this guy. Done. If I start with this domino falls and the next domino falls, I'm done. So what I get on this side, if I add it, I get k over 2 times 1 plus k plus 1. That is completely true. Nothing wrong with what I did. I assumed this is true, and then I added the same damn thing to both sides, so of course it's still true, right? But again, now I focus on what the hell should this look like? It should look like that. If I can make this look like that, golden. I can almost feel some of you guys like, what the hell is going on? I can feel it. It's weird. It's right there. It's like, what's going on? All right, we'll do another example. Don't worry. Don't worry too much. So now my whole focus is rewrite this to look like that. So what can I do with this? You take some of this out of here. It's too much crap. Paying attention to what I know it should look like. This is not too hard, but do you see how this should be a k plus 1 over 2? So take a k plus 1 over 2 out. That's the awesome thing about proofs. Is if I know a piece of it should look like this, just make it look like that. And then the rest of it better fall into place, or the whole damn thing is shit. We got to go back in time and smack Gauss around. And say, sit down and shut up, kid. Which would be bad, because then we lose a lot of what he did. So if I take a k plus 1 over 2 out, what's left on the inside? Now let me do this one step at a time. Let's take a 1/2 out. If I take a 1/2 out, what's left? Take k times 1 plus k plus. You take a 1/2 out. 2. And now take a k plus 1 out. It's just a little bit easier to do it one at a time. So if I take a k plus 1 out, what am I left with? K plus 2, which is exactly what the hell it's supposed to be. So assuming this statement is true for the kth term, and then proving that it's true for the next term, because it became what it was supposed to become. I know it's true for everything, because if it's true for the first case, this just showed me it's true for the second, which means it's true for the third, which means it's true for the 998,000th, which means it's true for the millionth, forever. Maybe. Now, I want you to realize that was an easy example of mathematics. But it's just getting used to it. I don't want to scare you too much, but it's just getting used to it. The steps hardly ever change. Notice how I cover my ass there real quick. The steps barely ever change, depending on what your first statement really is. Sometimes your statement will be inequalities, and there are some examples like that on the paper. So what I want to do is I want to do a couple of examples with you. I think I'm going to do number 1 and number 3 with you. And then I want you guys to do number 2 and number 4 on your own. And I love the look I'm getting. It's not a quiz. Who cares? Just do whatever you can. So let's do number 1 together and number 3 together. So what do I want to do first with number 1? Or let me say it like this. What should we do first? Your answer might be, skip it. What should I do first with number 1? Not the K thing. What I have to do very first thing? Sound like a psychological thing. Base case. I got to show that it's true for the first case. You can actually show it's true for the first several, just to see if there's even a reason to do it. If it's not true for 2, then screw the thing, right? But real quick, notice on number 3, we're not going to do that right now, but notice how it says n greater than or equal to 5. So your base case there would be 5, right? And so forth. So this one says for all n, natural numbers n, so 1 and up. So if n is 1, what does that statement become? Yeah, because 2 times 1 minus 1 is 1. So the list goes up to 1. Is that equal to 1 squared? Yeah. Yes. So the base case is true. Bless you. Base case is true. Now what do I do? Assume it's true for the kth one and write that out for myself, right? So assume SK, which should say what? What would SK say? Yeah, 1 plus 3 plus up to 2k minus 1 should be k squared. Assume this is true. Okay. And again, I want you to realize the disconnect is, I want to show two things. I want to show it's true for the first guy, and then I want to show if it's true for the kth one. That's why I can assume it's true. If it's true for the kth one, then it must be true for the k plus 1th one. If it's true for this guy, it must be true for the next guy. That's the case that makes it go all the way through everything. Okay. Good, good, good. So, assume this is true, we want to show what?
K plus 1.
So what would that say? 1 plus 3 plus 2k minus 1 plus... Yes, ma'am, sorry.
Does it have to, like, does it actually have to work? Like, because if you plugged in 2, it wouldn't work.
Let's see, 2. If you plug in 2, it's 1 plus 3 is 4, which is 2 squared.
Plus 3.
Huh? All right, so if I... so it's good. So let's do like I said earlier. Let's try it. Let's go beyond the base case. So I like that. You're like, well, he just said, is it worth my time? And maybe this thing is full of shit. And let's see. I appreciate it. That's awesome. So if n is 2, what does this say? How far up do I go? 1 plus... I want to go up to 2n minus 1. And what's twice 2 minus 1?
Oh, okay, wait, never mind. I see. Never mind.
I got you. So 1 plus 3 is 2 squared. That works. Cool. I don't know if you guys noticed, if you ever knew this, that all the squares are separated by consecutive odd numbers. What's 12 squared? What's 13 squared? How far apart are those? 25. The next one, 14 squared is 27 above that. The next one is 29 above that. The next one is 31 above that. That's really what this thing is all about. It's kind of nifty. Okay. Or not. So that we went beyond the base case, which is not a bad idea in general, just to get a feel, especially when it's really freaky shit going on. You want to do a couple just to see what really is going on there, concrete-wise. What's going on? Okay, so what's sk plus 1 going to say? It's not just going to stop here. It's going to go up to where?
2k plus 1.
2k, yeah, exactly. If you make k, every k you see k plus 1, it goes up to 2k plus 1. All right, let me do this again. All right. To get the kth term, how did we get the kth term? We plugged a k in for n, right? How did we get the k plus 1 term? We plug a k plus 1 in. And if we plug a k plus 1 in, we'll get twice k plus 1 is 2k plus 2 minus 1 is 2k plus 1. If you couldn't follow what I said, you could do it on your papers. If you plug a k plus 1 in, what's twice k plus 1 minus 1? 2k plus 1. Okay. If you don't believe me, go away. And what do I put on the other side? K plus 1 squared. Good. I'm just replacing k with k plus 1. What is k? Some number. Beautiful. I love it. So it's like 7. So what's k plus 1? It's like 8, right? So if I can put a k in, I can put a frickin' k plus 1 in all day long. I can put a k plus 11 in. Who cares? But I want to assume it's true for one of them, and then I want to show it's true for the next one. So that's k. This has got to be k plus 1. So on this side, it's going to be k plus 1 squared. You start to feel the rhythm here of how these things work. Next thing I'm going to do is start... I know this is true. I'm going to add what it needs here to both sides and then show that that becomes this. That's pretty much almost always what we do. So if I start with what I know is true, and that's sk. Oh shit, you're facing the other way. If I start with sk, and I add what it needs, 1 plus 3 plus 5 plus... So what's this guy need? What's he need here to make it the same as what I'm trying to show? 2k plus 1. Now here's another place people don't understand. I can't just write this and be done. I have to show this is true. So I start with this equality I know is true. I add what this side needs. The only thing I can do, because this is a known equality, is add the same thing to the other side. then I have to show that this, whatever the hell it is, becomes what it's supposed to be. Right? So if I add 2k plus 1 on this side, I get k squared plus 2k plus 1. But of course, what is this?
K plus 1 squared.
K plus 1 squared. Done. Done. Finished. We showed that if sk is true, we showed this is true. So therefore, for any of them, if it works, the next one works. Since it works for 1, and hell, it works for 2 also. It works for 3, it works for 4, it works for 18 billion. This one working means the next one works. This one working means the next one works. So forth. Yes, ma'am?
How did you get the k squared plus 2k plus 1?
Oh, what is on this side? K squared. What did I add to this side?
2k plus 1.
So I just add that to both sides.
Oh, I see.
Yeah, so I added this to that side, yeah. Because that I know I can do that. I'm completely, if I say this is true, I'm allowed to add the same thing to both sides. Addition property of equality. Yay. Now the new thing here is I just want to make this side look like what it's supposed to look like if this really is true. If this really is true, it's supposed to look like this. If I can't make it look like that, then the thing I started with is not true. Or I'm just not good enough at it, right? You gotta be careful. Don't just say, well, this must not be true, this must not be true. All right, so you guys try the second one, and then we'll do the third one together. I want to shut up for a little while. I've been talking for way too long. You guys do number 2. All right, so the one is 3 plus 11 plus 19. There we go. Cool. They don't give a lot of examples. And very quickly, before I forget, math induction shows up on page 699 very quickly, and they reference page 76 where they actually lay out the math induction. They don't give it very good examples, so I'm sorry about that. But there are a couple examples there for math induction. Good. That's what we
Yeah.
So then you start here, add what this side needs to both sides. And see if you can make what you get on this side when you add this to it, and you make it look like this. That's the idea. So if you don't know this is what you want to show is right. So you start with this, add what he needs. And if you add that to this side, you better add that to this side. Then you want to make this side look like that side, and then you're showing it. That's every time, just about. I keep saying just about. Almost every time. Okay. So then it's 2. Populates 16 minus 5. 11. So 3 plus 11 is 14. 16 minus 14. So remember, this is a sum. This just tells you how far to add up. So anything you do is 3. So for the 2 one, you're going to do 3 plus 11. If you put a 3 in, it's going to be 3 plus 11. So see how far to add up. Good. 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 So now we want to show this. So that means that you take what you know is true and you add what you need to it. If you add this to this side, you better add it to this side also. Yeah, because that's what he needs. If you start here, you want to show this is true. You make this side look the way it's supposed to, so you add this to it. But then you better add it to this, and then what should this side look like? It should look like that. So take this, add it to both sides, and make this side look like this. Oh, so what is this? What would it be here? What would be the next for k plus 1? Would it be 8 times k plus 1? Minus 5. And that would equal 4 times k plus 1, yeah. Minus. I like it cooked. So you have to, now you start to prove it. You start with what you know is true, and you add this to both sides. Then you'll have this side looks the way it's supposed to. But then you just make sure that this plus this equals what it's supposed to. That's what you got to show. So what? This is k though, right? Yeah. So plus what? What would the next term be for k plus 1? When you only put k plus 1 in, that would be this k plus 1 should go one more term up. So plus, what would the k plus 1 piece look like? Plug up the k plus 1 in. Oh, you got it. Okay, so put it here.